In this lecture, we talk about cellular homology of a CW pair. So you can find this material on page 137 of Hatcher. So you start with a CW complex. So say X is a CW complex, and recall, and we have explained it in multiple lectures, that how do we construct the CW complex. So you build it inductively. So what you do is you take cells and you attach it to previous cells or less dimension cells via boundary. So you take an n cell and you attach its boundary to n-1 cell. So this is the filtration on CW complex. So we have seen how to construct this filtration before. So say you start with 0 cells, then you take 1 cells and you attach the boundary of the 1 cell to 0 cell. So x1 consists of 1 cells as well as 0 cells, but boundary of 1 cell is attached to the 0 cells. Then you construct x2, you add 2 cells to the mixture, you take 2 cells, attach their boundary to 1 cells. So now x2 consists of 0 cells, 1 cells and 2 cells, and so on. So you have a filtration like this. So this filtration is important. So if you go on to read spectral sequences, you will meet this filtration of CW complex again. Now if you modulo out xn minus 1 from xn, what you have is just the n cells left. Because at every stage, for example at x2, in the mixture you just added 2 cells. All the 0 cells and 1 cells are contained before it. So x1 contains the 0 cells and 1 cells. So if you do x2 modulo out x1, then only thing you have left is 2 cells. So similarly, if you modulo out xn minus 1 from xn, this will consist precisely of n cells. And for a good pair, you write it like this: xn comma xn minus 1. So this is a good pair. And the basis of our pair is precisely these n cells which we have added. And these n cells sit in the nth part of our chain complex. So this is how the chain complex will look like. So Cn part will be non-zero, where you have the n cells, and everywhere else you will have 0. So you have n cells here. So now you just count the number of n cells, and that will give you the homology here. So the homology is 0 if k is not equal to n. If k is equal to n, you just count the number of cells sitting in. So now consider the long exact sequence of our pair. So this is the long exact sequence of our pair. So it keeps going on. So now if k is not equal to n, so if k is not equal to n, then look at this. So this will be 0 because k is not n. So use the result here, k is not n. If k is not n minus 1, then k plus 1 is not n. So if k is not n minus 1, this implies k plus 1 is not n. So since this k plus 1 is not n, this k plus 1 is not n, these two indices are not matching, this will again be 0. So notice that this index has to match this to get a non-zero homology. So this index does not match this, this index does not match this, because we are writing it like this. For k not equals to n and k not equal to n minus 1, these two are 0. So since this is a long exact sequence, these two are 0, so you have an isomorphism here. And therefore this hkxn minus 1 is iso to hkxn. Now if k is greater than n, then we can rewrite this sequence but with a different pair. So now we take the pair xn minus 1 comma xn minus 2. So obviously xn minus 2 lies in xn minus 1. You see the index is increasing. So you get a long exact sequence like this, which keeps going on. Now again, since k is greater than n, so since k is greater than n, so obviously that means k plus 1 is greater than n minus 1. So these two indices do not match. So this is 0. Similarly, this index does not match, because since k is greater than n, so this implies k is also greater than n minus 1. So you do not have equality. So since you do not have equality between this index and this index, you have 0. Because to have non-zero, you need to have equality k equals to n. So these two are 0, so you have an isomorphism here. So xn minus 2 is iso to xn minus 1. So you get the same iso here. So this iso right here is getting carried to here. So inductively you can keep forming newer and newer sequences by taking different pairs. Now, so this iso you got from here, this iso you copied here, this iso you got from here, and then you can form another pair. Now you form xn minus 2, xn minus 3, and so on. So you keep decreasing index and you will keep getting isos. In the end you will have hkx0, which is just the 0 map, because this just consists of 0 cells and you're talking about hk. So this is 0. On the other hand, if k is less than n, then we will have a new pair. So now you take the pair xn plus 1 comma xn. So this sequence will go on like this: xn, xn plus 1, xn plus 1, xn, and so on. So this will keep going on. So now here you have k is less than n. So if k is less than n, this implies that k plus 1 is less than n plus 1. So this index does not match this index. So if these two indices do not match, this is 0. So if k is less than n, it also implies that k is less than n plus 1. So k and n plus 1 do not match. So k and n plus 1 do not match. So this is also 0. So you have an iso right here. And this is the iso we are talking about right here. So you keep going higher and higher, and you can keep going higher. So if x is finite dimensional, so x is finite dimensional, and say its dimension is say some n plus m, so then this will be finally equal to hk of x. So our result is that if x is finite dimensional and you have k which is less than n, then hkxn, this is isomorphic to hkx. So obviously this xn via this filtration, this will be included in xn plus m, which we are setting as x. So this inclusion map for k less than n introduces this isomorphism. Also, if k is greater than n, so if this k is greater than n, then you end up getting 0. So in particular, say your dimension of x itself is n, then for k greater than the dimension of our given space x, you will get hkxn as 0. So if k is greater than dimension of x and say your x is just xn, then you will get 0 via this isomorphism. So again, you can read all these results on page 137. Now an important remark is that this filtration and associated these three sequences, one sequence, second sequence, and the third sequence here. So you can use these three sequences and fit them together to produce a spectral sequence. So the spectral sequence just comes from gluing these 1, 2, 3 together. And for further details, you can see online notes of Hatcher on spectral sequences.